Hey guys, Mr. Yusten here. Today I want to talk to you about chemical reactions. Now to start this off, I want to show you a chemical reaction. So here's a video.
In this next displacement, we are pouring colorless silver nitrate solution into a beaker containing a copper coil. We notice that as the silver nitrate solution touches the copper, the coil immediately darkens and thickens. Copper is reducing silver ions to silver. When we take a closer look, we can see the silver crystals on the surface of the copper. Now, after some time, we also notice that the solution has turned blue because copper ions are formed. Copper has been oxidized to blue Cu2+. As we shake the wire, we see the large amount of silver that has been displaced.
Alright, so this reaction is silver nitrate reacting with copper metal, and it's producing copper 2 nitrate and silver metal. Now, there are two distinctions here, the things that we are reacting and the things that we are creating. So the things that we are reacting are called reactants, and the things that we're creating are called products. Now, the things that we're reacting, that would be silver nitrate and copper. Those are the things we're reacting. The things that we're creating, the products, is copper 2 nitrate and silver. Now I'm going to write an actual chemical reaction for this. So I'm going to take these names of these substances and write the formulas for them. So this first one, silver nitrate, silver has a +1 charge, nitrate has a -1 charge. So that is AgNO3, just one of each. Okay, and the copper is an element, so all I have to do is write the symbol for the element copper. Now over on the product side, I have copper 2 nitrate. The charge on copper is 2, but nitrate is still a -1. So that means I'm going to have 2 of the nitrates here, balancing the charges. So we have CuNO3, parentheses around NO3, 2, and then we have silver metal. It's once again another element, so I'm just going to write the symbol for silver. Now you may also notice that I have this little AQ here, and this little S here. AQ here and this little S here. That stands for aqueous, which means it's dissolved in water. The S stands for solid. The copper is a solid wire. This is also dissolved in water, as you saw in the video. And then the silver is a solid as well. It forms solid silver. Now, if I were to actually draw a picture of this reaction, okay, silver nitrate is actually ionic, so it's actually got 2 ions here. So we have silver ion with a negative NO3 ion, polyatomic ion, attached to it. Copper is just a single atom. It's atomic. For the copper nitrate, that one actually has 2 of the nitrates with the +2 for the copper. So we have a +2 copper ion and then 2 nitrate molecules, an NO3 and another NO3 molecule attached to it because they have a -2 charge. And the silver is just atomic again, so a single atom. Now, looking at this picture, if you look at it carefully, I do have the same amount of copper atoms on both sides. It just changes its charge. I do have the same amount of silver atoms on both sides, but I do not have the same amount of material because this nitrate ion, an NO3, there's actually 2 of them here and only 1 of them here. So this is actually not balanced. In order to actually follow the law of conservation of mass, I would actually need another AgNO3 over here so that I have enough of the nitrate ions in my reactants to actually create this copper 2 nitrate. I need to have a second nitrate to be able to create it because it has to come from somewhere. But that does create a problem because now I have 2 silver atoms over here in this AgNO3, but I'm only creating 1. So I also have to, because I added this, have to add a silver over on this side. This now is balanced. It has the exact same number of atoms on both sides of the arrow. All the material I start with turns into something. Everything that I create comes from somewhere. So once it's balanced, I'm going to add coefficients in front of these reactants here. So for the AgNO3, it actually took 2 of those to do this reaction. So I'm going to put a 2 in front of it. And then for the copper, it just took 1 of them. I was only able to create 1 of the copper nitrates, but I was creating 2 of the silver atoms. So a couple of vocabulary terms to write down here. Reactants are the compounds that you start with in a chemical reaction. It's the left side of the equation. Products are the compounds that you end with in a chemical reaction, the right side of the equation. Subscripts are the little numbers that are in the chemical formula. So they represent the number of each element or the number of each ion in a chemical formula. For example, with the AgNO3, a subscript would be the 3. That's part of it, telling you there are 3 atoms of oxygen in there. Coefficient, on the other hand, is how many molecules of each compound you have in that chemical equation. How many did it actually take? So going back to the reaction here, this 2 is a coefficient and this 1 is a coefficient. This 3 is a subscript. This 2 here is also a subscript, telling you have 2 nitrates. Okay, a couple more symbols that are used in chemical equations when writing them. We have a plus sign, which is used to separate reactants from each other or to separate products from each other. We have an arrow, which separates the reactants from the products, and it always points from reactants to the products. Sometimes we include a little S or an L or a G to represent whether or not we're talking about a solid, a liquid, or a gas. So those are kind of next to, like a subscript. They're down below and next to it after the reactant or product. We also have something called an AQ. This means aqueous. So it's a solution. It's dissolved in water. That's what AQ stands for, aqueous. Now, it's important that we actually balance the equation. Both sides of the equation have to have the same number of atoms. And this is how we show the law of conservation of mass, that mass is actually conserved and we don't create anything from nothing. You can't destroy it either. Okay, so there's a couple methods in order for balancing an equation. I kind of showed you one of them there with the picture. That one was called the counting method. Okay, so the counting method is where we add molecules to each side of the reaction. We just kind of go back and forth until the number of each element is the same in both the reactants and products. So here's an example of this. I have the reaction separating water here. Okay, so here's the reaction. I'm going to start off by just drawing a picture of each and every single thing. So I've got my water here, which is 2 hydrogens and an oxygen. And then on the other side of this arrow, I have hydrogen, which is H2, and oxygen, which is O2. Okay, now if I count on both sides here, I have 1, 2 hydrogens and 1, 2 hydrogens over here, so that's the same. But then the oxygens only got 1 and 1. So what I'm going to do is I'm going to add to the side that has less. So this is the side with less. I'm going to add another oxygen, but I can't just add a single oxygen. I have to add the whole thing, H2O. Okay, so I have a whole nother water here, H2O. So now I've got my 2 oxygens on both sides, but now my hydrogen's off. So I'll kind of go back and forth over and over again until it's balanced. So since I have 4 over here now, I'm going to add another H2 here until I get 4 on this side. So now this is actually balanced and it's even. You just kind of go back and forth and just keep adding until you actually hit the point where they are balanced. So the coefficients here are going to be 2 for the water, 2 for the H2, and 1 for the O2. Now some pros for the counting method. It is very simple. All you have to do is count. But some cons for it, this can actually take a long time, drawing them out and kind of writing them out like this. It takes a lot of scratch paper, and you do a lot of this counting in your head. So the other method I want to show you guys here is something called the crossing off method. This is where you either write or draw out the molecules showing for each reactant here, and then you cross them out as you write them on both sides so that you can actually show that they're even over there. So let me show you an example of this. So this is the reaction of burning methane. Now I could actually draw these out like I did in the last one, but I'm going to show you a different way to kind of do this. Instead of drawing a picture like I did, what I'm going to do is actually draw C, H, 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 H. Just kind of list out a single element for each one there. So that's a CH4. Then this would be an O2, so OO. And then on this side of the arrow, I have a COO, CO2. And then I have an HHO, H2O. So I'm actually just kind of listing the elements and drawing out each one. Now what I'm going to do is I'm going to go back and forth and just cross off the same element on both sides. So I have a carbon and a carbon. I have a hydrogen and a hydrogen. I have another hydrogen and another hydrogen. And now I'm out of hydrogens. Okay? Oxygen and an oxygen, oxygen and an oxygen. So now I'm going to look at what is not the same on both sides. So I have no more hydrogens to cross off, but I still have hydrogens over here. And I have no more oxygens on this side to cross off, but I have an oxygen over here. So I'm going to start with the hydrogen. Just do one element at a time. This hydrogen here, I have 2 of them to cross off, but none to cross off over here. So what I'm going to do is I'm going to add another HHO, and that allows me to cross off my hydrogens on both sides. But I have a problem with my oxygen still. So this is an O and an O on this side, which I can't cross off over here. So I'm going to add an O and an O over here, so I can actually cross off both oxygens on both sides. And once I've been able to cross all of them off, that is how it balances. It's 1, 2, 1, 2. So some pros for this one. It is very simple. It's very easy to do. You don't have to think a whole lot. I mean, you just basically keep crossing off until it's there. Also, another con with this, though, this takes a long time. This is actually the most time-consuming method, either drawing them out or writing them out like this and then crossing off each element, going back and forth. Again, it takes a lot of scratch paper, and I have noticed that if you do mess up somewhere, like you notice you made a mistake, you kind of have to just start all over, which can be a problem. But it is almost foolproof if you don't mess up. You just kind of go back and forth until they're all crossed out, and then you have it. Now, the last method here is something called the factor method. What you do here is you create a little table, a T-table. It lists the atoms for each element in both the reactants and the products, and then you multiply by factors to make the number of atoms for each element equal. And then these factors eventually become the coefficients. So here's an example of this. This is the reaction of making ammonia. Okay. So to start this off, I'm going to create a T-table right here. This is my reactants. This is my products. Okay, and then over here I'm going to list all of the elements. So I have nitrogen and then I have hydrogen. Okay, there's just 2 elements in this reaction. So my reactants here on this reaction side, I have 2 of them. And then I have 2 of these. Over on the products, I have 1 of the nitrogens and 3 of the hydrogens. Now it's very clear to see that I do not have the same number on both sides. So what I'm going to do is I'm going to try to fix that. I'm going to start with the nitrogen. Since this is 2 and 1, I'm going to times this by 2. And by timesing this by 2, I'm going to times everything in here by 2. That means I now have 2 nitrogens and 6 hydrogens. Okay? So now I have 2 and 6, so my nitrogen's fine, but my hydrogen's not. So I'm going to come back over here and go, okay, well, what do I need to actually make a 2 into a 6? Well, that's a factor of 3 here. So I'm going to times this by 3, and that will times this by 3, giving me 6. So now I have 6 and 6, 2 and 2. So these things I used right here are the coefficients. 2 of these, 3 of these, 1 of these. Now some pros to this one. It is very quick to do. It doesn't take up a lot of space. It's just kind of going back and forth really quick and doing some math in your head sometimes and writing it down. The cons, though, this is the most complicated. It's not quite as easy to do. It does take some practice, but for some people, they like the less writing and they like the quicker ability to do it. So it's not quite as easy as to see exactly what you're supposed to do here. So you may use whatever method you want to actually do your balancing. It does not matter as long as you can actually get the result.